So here's video number 3, where we're going to calculate what's called the initial rate. Incredibly similar to the instantaneous rate, but now we're going to find the rate at time equals 0. Same process as finding instantaneous rate. The only difference is that we're drawing a tangent line where it's going to be tangent to t equals 0. So I'll show you what I mean with this. Here's that exact same graph as we saw before, but this time we're going to be calculating the initial rate. So I've already moved my ruler so that I placed my ruler so that it is tangent to t equals 0. And we'll notice when we draw our tangent line this time, it's going to be a lot steeper because the reaction just started to happen. And since the reaction just started to happen, it's going to be moving faster because we're going to have more particles present, therefore we'll have more collisions, and it's going to cause the reaction to go faster at time 0. 25 minutes, I'll have less particles present, and therefore I will end up decreasing the rate of reaction. So I'm going to extend that line a little bit further here. And I'm going to drop it all the way down to the x-axis so I can have two really simple, easy points in order to figure out the slope of that line. Because once again, the slope of that line is going to give me the initial rate when the reaction just starts. Move my ruler out of the way. Go away, ruler. And then I'm going to choose 2 points to find the slope of this line. Or I can do rise over run. Either way works. I'm going to choose my run here is going to go this way, and my rise here is going to go this way. So when I am beginning to estimate some values here, my run is going to be, I'm going to guess 25 to 0, so it's going to have a change in time of 25 minutes. Ironically enough, just kind of like the last problem where we found a new rate. And then my rise is going to be about 5.5 moles per liter minus 0, so I'm going to have 5.5 here. So to find the slope of the line, which is going to be the initial rate of reaction, the rate is going to still be change in concentration, which is my rise, divided by the change in concentration, which is my run. So I will have 5.5 divided by 25. And you might notice that I'm not doing a really good job with significant figures here. And it's mostly just because that's not the point I'm trying to get across. 5.5 divided by 25. I will have a rate of reaction to begin with of 0.22 moles per liter for every second. If we think back to the previous video, you'll see that that's going to be a lot faster than what we calculated the first time around. So with that, let's take a look at a good IB sample problem, which will do all 3 of these different rates: average, initial, and instantaneous. So once again, ignoring the watermark here because Ms. J forgot to pay for her software. Here's going to be our example problem. It says the graph below shows the evolution of oxygen gas produced when hydrogen peroxide decomposes. We're going to write a balanced chemical equation. The other product is going to be water. We're going to calculate the average rate of reaction, which is going to be just the final concentration minus the initial concentration divided by the change in time. We're going to calculate the instantaneous rate of reaction at 10 seconds, and then we're going to calculate the initial rate of reaction. This is a typical IB problem that they would be asking you. So let's start with the equation. To write an equation for this, I'm going to first know what the equation for hydrogen peroxide is. It's H2O2. And this is one of those types of chemical equations for a chemical that you're just going to have to remember. It's going to decompose into water and oxygen gas. And I'm going to balance this equation here. So to balance that equation, I'll put a 2 out front to make 4 hydrogens. I'll make 4 oxygens, and now it's balanced. So to be perfectly careful with this, I would put states of matter here. This would be liquid, this would be gas, and this could be liquid or gas or aqueous, and I don't think it really matters. I'm just going to put liquid. Next question is to find the average rate of this reaction. The average rate is going to be erroneous because if I look at where I just put my ruler, where I do final molarity minus initial molarity, you'll notice here that that straight line no way tells a story of what the oxygen is doing as it is created. This curve is definitely not equal to the rate of change that I'm going to make with that straight line. But they're going to ask you to calculate it anyways. So I'm going to make my line that is no way tangent to the curve. And I can depict a couple of points here in order to find my average rate. This is going to be at 60, comma, and we'll call it 0.0025. And this is going to be 0, 0. So my average rate is going to be the change in concentration divided by the change in time, which is going to be the 0.0025 minus 0, all divided by 60 minus 0. And when I throw that into my calculator, I'm going to get another really small number that's a good idea to put into scientific notation. And I'm going to do this with incorrect sig figs, but that's not the point I'm trying to get at this evening. 4.2 times 10 to the negative 5th moles per liter seconds. Don't forget your units when you write these rates. All right, so that's the average rate. Now the next thing I'm going to do is I am going to find the instantaneous rate at 10 seconds. So what I've already done is I've taken my ruler and I have placed it at t equals 0 at 10 seconds, and I'm going to draw a line that's tangent or only touches the curve at t equals 10 seconds. So here comes my line, and I'm going to adjust it a little bit here. And when I find that slope at the line, it's going to give me the instantaneous rate of reaction at t equals 10 seconds. So I like to drop it all the way to the y-axis because it will give me a nice value which contains 0, makes my calculations easier. I'm going to now just make some estimations on some points where the line is hitting. This looks like, oopsie, this looks like it's hitting at 0, comma, and I'm going to make an estimate here. I'm going to say that that's about 0.00020, just as an estimate here. And that's this point right there. And then I'm going to go over here, and this looks like it's at 30, comma, 0.0025. So at 10 seconds, I'm going to find my rate, change in concentration divided by change in time. So I'm going to do 0.0025 minus 0.00020, all divided by 30 minus 0. throwing that into my calculator. 0.0025 minus 0.0002 divided by 30. Again, really, really, really small number, and you're going to find a lot of these here. I'm going to have 7.7 times 10 to the negative fifth moles per liters seconds. Okay, so there's your instantaneous rate. All right, last but not least, we're going to find the initial rate. And I'm going to put this right directly onto the graph because I'm going to avoid that watermark. So I drew a tangent line that is tangent to t equals 0. And the nice thing about initial rate is one of your points is always, always, always going to be 0, 0. So there's my first point there. It's going to be, come on, right, 0, 0. Then I'm going to find another point here. This looks like it's at 20, 0.0025. So to find my initial rate, my rate, capital R, is going to be 0.0025 minus 0 divided by 20 minus 0. And when I calculate that out, you notice that my initial rate is going to be a lot higher than my instantaneous rate at 10 seconds because the reaction just started, more particles present, meaning faster rate of reaction. 10 to the negative fourth moles per liter seconds. So one of the questions that they could ask you from this is which of these is going to be the one that does not accurately depict the rate of reaction, and that would definitely be average rate because the change in concentration will constantly be changing over time. So hopefully this will help you do your practice problems that are coming up, and thank you. Have a great evening.